Hi everyone. So in this video, we'll be talking about DeepSeek a little more. Basically, we'll be talking about reasoning models and how the GRPO algorithm, the group relative policy optimization algorithm, has been used for building reasoning models, and how you can actually build your own reasoning model for your own custom application. So for DeepSeek, like in the previous video, I talked about DeepSeek and the approach they took for uh, their training purposes. So let's just rewind it a bit. So for they had their base model DeepSeek V3, which was a 671 billion parameter model, uh, out of which 37 billion parameters were activated. And then they just did pure reasoning with reinforcement learning, where they used the GRPO algorithm and a rule-based reward system, through which they got their first reasoning model, which was the DeepSeek R10. But here they had a few problems. Number one was that it gave outputs in multiple languages, so it hallucinated with language recognition. And other than that, I think it was like the formatting was not correct. Sometimes it gave responses with the given format, sometimes it didn't. And then DeepSeek, then they took the approach that they again took the base model. First, they implemented the supervised fine tuning. Now, supervised fine tuning is just similar to supervised learning, where we give the model the labeled data and ask the model to just learn from the data. So uh, the DeepSeek, they took around 600,000 reasoning examples. Reasoning examples were the examples which had question, answer, and the chain of thought, the reasoning behind the answer to that question. And then they had the non-reasoning examples, which were 200,000 in numbers. So it's just Q&A. So they had this complete 800,000 supervised fine-tuning data set, and then they implemented RL on that fine-tuned model. So they first had the base model, they fine-tuned it for reasoning, then they implemented reinforcement learning with GRPO, and then they got their final model, which was the DeepSeek R1, which we all use right now with from their API or at their platform. So let's talk about supervised fine tuning. So as I uh, mentioned earlier, that it is the most basic approach by which you can fine tune LLMs for niche applications. It is ask the LLM to learn by looking at a lot of examples. So there are two types of learning. One is like learn by uh, looking at examples, and then second is learn by trial and error. So for supervised fine tuning or supervised learning to say, it's you give input and you show the model the output for that input, and then model tries to replicate that kind of outputs for similar kind of inputs. So that's why now model the data set sizes can vary from 1,000, 10,000, 100,000, or like any number depending on the size of the model and the number of parameters you want to tweak in the model. So the process for supervised fine tuning is very simple. It's the easiest way of fine tuning a model. You prepare a labeled data set with niche examples. Then you initialize the model, and then you just implement a gradient based optimization, which are the weight updates based on the loss function. And then in this, most of the time you do LoRa fine tuning, which is basically you just tweak limited parameters in the model. You're not doing full fine tuning most of the time because that's not efficient, or that required a lot of compute. So it's parameter efficient, it's compute efficient, so you do that. Now for SFT, you are mostly dependent on data, like you are heavily dependent on data because there is no engineering other than that like based optimization is like the base algorithm for almost every learning. Then you calculate the loss with the help of backpropagation, and LoRa fine tuning is also not like these are things that you are just doing to optimize. Like you're not doing these things to optimize anything. These are just the basic steps of supervised fine tuning. The whole engineering would be in the dataset prep. Like for say if you are building a medical dataset, then you need a lot of human data right there. Now, what I mean by human data is you need real world data, because today what most of the problem, like what the major problem in data prep is that We try to prepare data with the help of LLMs. Uh, so that's the synthetic data generation that we try to do. And in synthetic data generation, what we get the problem, what's the problem is that the data is very redundant. Like if you see every other example is it will look similar when you generate data with through LLMs. So that is a problem. So you need a lot of real world examples to get a very good supervised fine-tuned model. Now the next approach is reinforcement learning. Reinforcement learning is the making the model learns through trial and error. For reasoning, there is in for reasoning models basically for models like these, which gives outputs like for a question. If you ask a question, they'll respond in a think block. They'll think for a bit and then respond for the answer. For these kind of models, you need a policy like DeepSeek used a policy-based algorithm. For a policy-based algorithm, we they used GRPO. GRPO is an update for an already existing policy algorithm, which was PPO. So PPO is proximal policy optimization. So let's first discuss about PPO a bit before jumping on to GRPO. So in PPO, you give it a question. The question goes into the policy model. The policy model generates an output, and then output goes into three different models. Now there is a reference model, there is a reward model, then there is a value model. A reference model and reward model combines and KL divergence. We perform KL divergence on reference model and the reward model outputs. Now, what is KL divergence? KL divergence is basically a penalty which ensures that the model is not going a lot, like it's not heavily going the distribution. Like when a model outputs something, there is a distribution chart. So model is not diverging a lot from its actual what it meant to do. For example, if a model is rewarded for polite outputs, like we are fine tuning a model, we are training a model to give very polite outputs. So it can perform like it can like start giving outputs like thank you every time. Like in each token, it's just giving thank you just to hack the reward. So to avoid that, we perform a penalty of KL divergence so that the what was the actual purpose of the model, it doesn't lose that. And then we get a reward from here. And from a value model, we get a value for the output. And then the reward and the value are then journalized basically to get an advantage term. Now, what is that advantage term? The advantage term is basically it's a rating for the output. So you can say like reward is also a rating for the output only, but advantage term is a much more optimized rating for the output. Now, in PPO, the policy model and the value model, these two models are the trained models. So these two models, both these models need to be loaded into the RAM, and that's why PPO is a bit compute efficient, memory efficient. Oh, sorry, not efficient, compute and memory heavy, and it also require a lot of VRAM to perform PPO. That's why they used something known as the GRPO. GRPO is Group Relative Policy Optimization. So in the name only you can see group. So that means we will have grouping somewhere. So here again, question comes in, goes into the policy model, and then from the policy model, we generate a list of options, list of outputs basically. For a query, we have multiple outputs for each query. Then these outputs goes into the reference model and the reward model. Reference model here is the base model which we are using. Say you are fine tuning, say you took a base model of Llama 3.18b, and that would be the reference model here. And then reference model. Now, from reference model, we do the KL divergence, the penalty which we discussed above. This KL divergence, which avoids the model to diverge a lot from its base nature. And then from the reward model, we generate all the rewards for all the outputs from all the outputs for the given question. Now, after that, we have all the list of rewards. Then a group computation, we perform a group computation, which is basically average estimation only. We just average for all the rewards and get a advantage term. Advantage term again acts as a rating for each response. You can also call it normalized reward. So it's basically for each reward, we subtract the mean of all the rewards and then divided it by the standard deviation of the rewards, and we get the advantage term. Now let's dip bit. Now let's let me explain it with an example. So let's say you have a prompt, Elon is the. So it's Elon is the. Now you can have a lot of completions for this given prompt, given question. You can have Elon is the goat, Elon is the evil leader, optimist. Like these are the four options. You send these completions into the reward model, and the reward model, according to the reward functions which you have set according to your like your personal choice, there would be a number of rewards. Like there would be one for goat, zero point 0.4 for evil, zero point 0.8 for leader, 0.9 for optimist. Then again, averaging these rewards, you will get some advantage terms. And here you will perform the KL divergence. KL divergence is basically the base policy, the pi theta, and the reference policy, pi ref. These two will be used for computing the KL divergence. And then you will subtract this KL divergence from the advantage term, and you will get a mean. You will mean it up, and you will get the objective. This is the objective which you have to optimize to optimize the policy of GRPO. So if you look at this equation, here we are getting number of outputs. We are getting a lot of number of responses for a question queue, and then we are calculating here. This is the pi theta by my pi old, that is the pi from the pi reference, from the reference model. Then we are using a clipping term here. This clipping term is nothing but we are just avoiding very confident outputs. Let's say for any advantage term here, we get an advantage of like maximum, like more than what we desire for. So we just avoid overconfident ratings by the model for any kind of for any completion. And then this is the KL divergence term, which we talked about. Um, this is the thing that we subtract. This is the penalty which we subtract from the model. This basically computes the distribution of the model for each completion. And if the completion is going a lot different than the initial distribution of the base model, then we just kill it. We just uh, penalize the model for those kinds of completions. And then this is the advantage term calculation, which is the for each reward, just subtract the mean and divide by the standard deviation. And this is the complete GRPO basically objective, which we need to optimize the policy and to maximize the policy and to just maximize the reward for the model. And then what is the difference in between GRPO and PPO? So in GRPO, we have grouped outputs. Like as you see, for every question, we have a list of outputs. Then there is no value model, so less computational. Like it is compute efficient. We can like easily run it. We run GRPO algorithm on data, and then KL divergence is done on the policy outputs rather than the reference and reward model outputs, which were done earlier in the PPO algorithm. And so, yeah, so we discussed about the GRPO, we discussed about the PPO. So now with the GRPO, one thing, let's look at some code now. So this is a basic Google Colab notebook, which you can easily get on the Unsloth website. It's on their website. They have put out for SFT and for GRPO as well. You just pip install these. You can run it on Tesla T4 also for free. So you can just check it out. You can just run the code, the base code. You can tweak it a bit, and you can just see what you can do. So here you just load the model. Uh, yeah, here just you first just we just patch fast language model, and then just here you load up the 3.1 ADB instruct. It will be loaded in 4-bit quantized, and then after that, what you can do is yeah, set this max sequence length to a little lesser. LoRa rank should be same. 32 is what you should prefer. Random state you can update it to 3407. I guess in the notebook it's 42. Then these are the target modules. This should remain the same. It will load up the model, and it will take a little time. And then yeah, from here you have to see how to like uh, load the data set. So no, not this. This was my addition. from here you can see. So here you prepare the data. You basically, there is a system prompt which tells the model how it should respond. Then this is the XML formatting in which we are again telling the model how it should respond. Or we are also checking this with the help of this XML COT format in our reward functions. Uh, this is the XML answer. This is the extracting term. So in the base, in the actual notebook, they have used GSM 8K dataset from OpenAI, which is, I guess, on journal math questions. So they just loaded the dataset from Hugging Face, mapped it to system prompt and questions, mapped it to questions and responses, extracted the answers, and prepared the dataset for further training. Mm, yeah, so they just got it from the yeah. Um, so I'm not using this GSM 8K. I'm using my custom dataset for my own experimentation. So I have these JSON files. If I show it like this, I have these questions and responses which I have, and I am using this dataset. Now, what you can do is either you can have a dataset with just questions, or you can have a dataset with questions and answers. So with just questions, like it depends on your reward structure basically. So for example, in reward in their base uh, collab notebook, they have correctness reward function. Here they are just uh, here they are just matching the question and the answer. So in math questions, you generally have a response as a number which is fixed. So you just match the responses and you just see if it's correct or not. So you can check correctness by that. But if you are using it for some other uh, purpose, then this doesn't make sense. Like say if you are using it for medical responses. So in medical responses, the output would be different, like generated by the model you are training and the base response which you have saved in your database in your data set. Those two might not match. So this doesn't work there. Then they have the int reward function, which is if the response is as an integer, they would give a zero point 0.5 reward to the model, which again uh, doesn't like really fit into most applications. It's just um, like cost. It's just specific to a math model, math specific data set. Then this is what I have added, a string reward function, which is reward the model if the output is in string. Again, this is of use in some cases. Then again, like you have to like figure out what are the reward functions for your particular use case would be, and you have to try and test on which reward models the model will perform better. Then this is the formatting reward function. They have two reward functions for format. One is the strict format, and then there is a soft format reward function. For strict, they have used like it should be of this pattern, then give the 0.5 reward, or else the reward should be 0. In soft format, they just said that if any of these tags are available in the given response, then just give the reward of 0.5. And then uh, this I have added. So basically what I'm doing is I'm just calculating the response. So I need long responses. So what I did is that if the reasoning tokens are greater than 400 and the response tokens are less than 200, I'm giving it a reward, and else I'm just giving a zero reward to the model. So it's just an optimized way of it's just like I'm just experimenting with this. I don't know how effective this would be, but I need more reasoning tokens for my application and less answer tokens. So that's why I'm giving model reward and trying it. Like I'm just hoping that it might learn from it. Then this is the count XML, which will be used for XML count reward. This function is just counting the number of XML tags in our complete response, like how it's responding for this, like what we are asking it, reasoning, closing tags, and then answering opening tag, and then answer closing tag. So like there should be four, like how many it's getting, right? So that's why that's how we are just giving it these rewards of 0.125 for each every tag. Then there for the correctness reward, like here they were giving it just by pattern matching and seeing what the answer is directly matching the answer. You cannot do it for a lot of applications because an LLM would give different outputs for a similar input each every time. So what you can do, try and do is what I'm experimenting with is you can just create embeddings for the response created by the training model, and you can generate the embeddings for the base response. And then you can just cosine similar, you can do the cosine similarity between those two responses, and you can just give the rating by that. So in dataset, how you can do is like in code, you can how you can do is you can use a embedding model, and for a response you can create the embeddings for every response, and then you can create answer embeddings for that question. So whatever that question would be. So for each response you do this. Like if you give it a question, and if you have a response, you generate, if you have response R1, then you generate embeddings for R1. You have embeddings for the answer for that question. You do the similarity matching. Whatever the similarity score is, you either assign that similarity score as the reward, or you can multiply the similarity score by 2 and then give it as a reward to the model. This is again experimentation. You can experiment with multiplying it with 5, or you can just directly try giving the similarity score as the reward also. So whatever works for you works for you. You can just test and try a lot of things. Then we move on to uh, the training part. So here is the how you set the parameters to train the model. Use VLLM. You can make it through to just, if you're using it on Google Colab, this doesn't make sense. If you are running it locally, then just put it through and it should work. You have to import, I guess, pip install VLLM. Here, yeah, you have to pip install Unslot VLLM, because it's required. And then you can just run with true VLM true. It'll just uh, makes your training a lot faster by almost 2 times. Then learning rate, keep it uh, here only 5e minus 6, which would be around 0.0005 something, 0 point, like after 6 digits 5. um, and then these are just some uh, base things. You don't have to change these. Don't change the LR scheduler type. Optimum should stay the same. Logging steps should be 1 is good. B16 float, FP16 should stay the same. Like if you are just running on Google Colab, just don't touch anything. It's fine. For device trained batch size should remain 1. Even if you're running it locally, keep it 1 only, because if you increase this batch size, it might just give you a code out of memory error. Like I'm testing this on a 48 GB VRAM, and there also I put it like I increased it to 4. I first increased it to 6, then to 4. On both times I got the CUDA memory error, so I'm doing it right now on 1. Then gradient accumulation step should be 4. It, like in the base notebook it's less, but mm, make it to 4. Number of generation 6 is fine. Decrease it if again getting CUDA out of memory. Max prompt length and max completion length, adjust it according to your use case. I increased it because of my particular use case. Then number of epochs, again, you can kind of calculate it with the help of um, you can calculate max steps basically with the help of training epochs and your batch size. So it's something with the calculation of like uh, I guess number of training epochs multiplied by or divide by training batch size and into I guess 1000 or something like that. And you can just Google it and you'll get the formula of calculating the max steps. Um, Keep training epochs from 1 to 3 only. Don't do 4 or 5, because it will just increase the number of steps for your training. And then save steps is basically after how many steps you want checkpoints saved. So if your max steps is 3000, just increase it to like say 550 or something, because that makes a lot more sense than 250 or something. Then output directory is outputs, and then report to, you can use weights and biases. You can just instead of none, you can just write V and B, and with this what you will get is you can see your outputs on weights and biases. You can create an account and you can log in into it from the notebook as well. Notebook only. It's a very short script. You can get it on weights and biases documentation. And here you can see different reward functions working on your um, how they are working on the data. You can also get GPU stats, and you can also get the loss function, reward function, and all the training required, like all the things which you want to see during the training of your model. You can just watch them from there. You can just have a look at that. So it's good. Then this is the GRPO trainer. Basically, this is the main uh, function where the GRPO would be implemented. So model is initialized, tokenizer is initialized, all the reward functions are initialized, training arguments and the dataset has been given. And when you run this block, the training will start. So it will start something like number of examples, then number of epochs, batch per size, gradient accumulation steps, like all the stats would come here. You will just see. So here you can see number of trainable parameters are only 83 million because although the model is about 8 billion parameters, but still only this much uh, parameters have been trained. And then further, there is this code block where you can run the base model, which is the actual model which you were training. So in this book, it's in this collab notebook, it's the Llama 3.18b, and then you can just save your LoRa model in the directory, and then the model you fine tuned or to say trained, and then you can just use that to generate outputs. And then there is some extra optimization things right below that, so you can just check it out also. It's a very basic way, like you can just run the base collab and you can get the idea of how to do everything. Now for dataset prep, if you will use it for some custom application, so preparing data would be the most important part of everything because the rest of the things are already available out there. So two are the major bottlenecks for training your own reasoning model for a niche application. That would be number one is the data set, the quality of the questions, and number two would be the GPU requirements. Basically, if you are training a 8B model, you need a lot of GPU computation to do that, like at least 48 GB VRAM. That is what I would suggest because I'm experimenting on a 48 GB VRAM and almost 41 GBs is exhausted during training only, and a lot of times I just hit the CUDA out of memory error. So just keep that in mind, and also don't take a lot of examples. Like if you are preparing a data set like this, don't go for examples more than 2000. I would suggest 1000, keep it under 1000 because there is one recent paper also that is S1K dataset, S1K scale time compute paper. In that they showed that how they achieved reasoning capabilities just with the help of 1000 examples. And they just focused on three things, which was the difficulty, then the good quality, and the diversity of the question. So these three things would help a lot. So basically, you need a very good quality of data. You need a good GPU, and then you can just run and you need reward functions. Like your reward function should be good enough, which could teach the model how to perform. So these are the things that you can um, look at, and you can get good reasoning models for your custom applications. So yeah, that's all for today, I guess. And yeah, I'll just attach this link for the Excalibur uh, in the description, and the links to Unsloth notebooks and to other resources as well in the notebook. Thanks for thanks for your time. Goodbye. Thanks.